Welcome, everybody. In this explainer, we're going to step into the plastics testing lab to really get a handle on three fundamental tests that every single plastics engineer needs to know. These tests are the absolute key to figuring out how a material will behave under heat, both in its final form and, just as importantly, during manufacturing. Okay, so let's dive right into this with a real-world problem engineers face every single day. You've got to design a car dashboard. Now, you know that part is going to sit in a hot car, baking in the sun day after day. Picking the wrong material isn't just a quality issue, it's a complete failure. So how do we make that choice with confidence? Well, the answer is in the data we're about to collect. So we're going to tackle this by breaking it down into 5 clear parts. We'll kick things off with the challenge itself. Then we'll walk through 3 essential lab tests: heat deflection temperature, Vicat softening temperature, and the melt flow index. And finally, we'll see how all this data comes together to create a material's unique thermal fingerprint. All right, so here's the crucial point. We start with these little raw plastic pellets, right? But our end goal is to create a reliable, high-performance part. A plastic's thermal properties are what get us from A to B. And as an engineer, you need precise tools to measure and really understand what's going on with these properties. And this is exactly why we test. I mean, even tiny variations in a batch of material can totally mess with how it flows into a mold, how it holds its shape over its lifetime, or even its final color and finish. These tests are your toolkit. They're for quality control and for making sure that the plastic you've picked is perfectly suited for its job, whether that's a simple toy or a critical part in a car engine. Let's head over to our first lab station and see how we can start to build up our understanding of a material's limits. We're kicking things off with the heat deflection temperature test, or HDT for short. This one is all about performance under load. Now, that definition is super specific, and for a good reason. This test basically tells you the maximum service temperature for a plastic part that has to support some kind of weight. See, it's not just about heat, it's about heat and pressure working together. At what exact point does the material just give up and start to deform? That's what we need to know. So try to picture this. You have a small plastic bar that's resting on 2 supports, almost like a tiny little bridge. This whole setup gets submerged in an oil bath that's slowly getting hotter and hotter. And all the while, there's a specific, calibrated weight pushing down right in the middle of that bar. And this lays out the standard procedure perfectly. It's a controlled, repeatable way to measure a plastic's short-term heat resistance while it's under a specific load. We heat that oil bath slowly and consistently, and the very moment that bar bends by just 1/4 of a millimeter, bam, we found our number, the heat deflection temperature. Okay, on to our second test. This one looks at softening from a slightly different angle. This is the Vicat softening temperature, or VST. It's less about the whole part bending and more about when the surface itself starts to get soft. So instead of bending a bar, what we're doing now is measuring the exact temperature where the plastic surface becomes soft enough for a weighted, flat-tipped needle to press into it by a very specific amount. It's all about measuring localized softening. And again, the procedure is very, very precise. The sample goes under the needle, a load is applied, and the temperature goes up at a controlled rate. The second that needle sinks exactly 1 millimeter deep into the surface, that's it. That's our Vicat softening temperature. This number is absolutely crucial for quality control, especially when you need to make sure every batch of material is consistent. So what's the real difference here? It all comes down to the type of failure we're measuring. HDT tells you the temperature when the entire structure starts to bend or deflect. VST, on the other hand, tells you the temperature when a single tiny point on the surface gets soft enough to be indented. They're both measuring how a plastic reacts to heat, but they're giving you 2 different but equally important pieces of information. All right, our final test moves us away from how a plastic performs in the real world to how it behaves during manufacturing. So let's head over to the melt flow indexer. This test is all about processability. Okay, in simple terms, MFI tells you how runny or thick a plastic is when you melt it down. The best way to think about it is like the difference between pouring water versus pouring cold honey. A plastic with a high MFI flows super easily. It's great for filling up those tiny, intricate molds. A low MFI plastic is much thicker, more viscous, and you'd use that for things like extrusion for making larger, more robust parts. This slide right here shows the actual machine. You can see this vertical cylinder. That's where you load the plastic pellets and heat them up to a very specific temperature. Then you have a piston with a weight on top that applies pressure, forcing the molten plastic out through a tiny little hole or die at the bottom. So following these steps gives you a precise, repeatable value. You heat the machine, load the plastic, apply the weight, and then you start a timer. You collect the plastic that squishes out over a set period, you weigh it, and then you use a simple formula to calculate its flow rate. This number is what helps you tell the difference between grades of a polymer and predict exactly how it's going to behave in your machines. And this is the simple formula you use to calculate the MFI value. So why the number 600? Well, that's just there to standardize the measurement. Since there are 600 seconds in 10 minutes, this formula just converts the mass you collected in, say, 30 seconds into the standard unit, which is grams per 10 minutes. It just makes sure everyone in the industry is speaking the same language. But you have to remember, if you want an accurate result, you've got to control your variables. If the machine isn't preheated just right, your flow will be all over the place. If your plastic pellets have any moisture in them, you'll get bubbles, and that'll throw off the weight. And if you don't pack the pellets down properly to get rid of trapped air, that can also lead to errors. You know, in a lab setting, precision is everything. Okay, so we've done our 3 tests. We've got an HDT value, a VST value, and an MFI value. So what do these numbers tell us when we put them all together? Well, they give us a unique profile of the material, its fingerprint. Together, these results create that thermal fingerprint for a specific plastic. The HDT tells you its structural limit under heat, the VST tells you its surface softening point, and the MFI tells you exactly how it's going to behave in the molding machine. With this fingerprint, you have an incredibly powerful snapshot of its total performance. And at the end of the day, this is why it all matters. This data ensures that the plastic parts in our cars, our electronics, and our homes will hold their shape and do their job safely and reliably under real-world conditions. It's the science that makes all our modern products possible. And that wraps up our look at these core thermal tests. The next time you see any plastic product, from a simple container to a complex machine part, just think about the data and the engineering that went into picking the absolute perfect material for the job. Thanks for joining me in the lab today.